And so, example in here. Given a system of figure, I will draw this figure. Design a PID so that the system operates with a peak time that is 2/3 that of uncompensated system. At 20% overshoot with 0 SS error. We have three conditions. For example, if a peak time is equals to the what 3, and so we need to reduce it to the what to the 1, okay, or 2 divided by 3 times our peak time. And also we need to satisfy the 20% overshoot in here, and also we should give the 0 steady state error. Okay, do you understand that? Okay. And so our system is RS minus 1, and we have the K proportional coefficient S plus 8 divided by S plus 3, S plus 6, S plus 10. Okay? For this case, we have unity feedback, nothing more. Okay? And so, in order to solve this problem, we should write what the step 1. At each case, we solve one problem, and step by step solution can be done by using these terms. Okay? And so for 20% overshoot, we should utilize the what the zeta, which is equals to what minus ln percentage of cos divided by 100, and also we have the square root of the pi square plus ln square percentage os divided by 100. Okay, these are the formulation. And so if you put the 20% in here, and then we get the zeta is equals to the what 0.456. Okay, we found zeta, and then now find the dominant pole at root locus. In the root locus, we have such kind of graph. For example, these are the root locus cases in here. For example, the red line are the root locus, and so at each root locus we have this kind of lines, and so each kind of these lines, for example, this represent 0.1, this is represent 0.2, and this is represent 0.5. Okay, in the root locus we show this, we see this. Okay, and so at each gain of k different line in here, and after that maybe we can find the zeta is equals to the 456. We go to this point, and so this point shows us to what one pole and one k value. at the root locus. Okay, and so if we solve this equation, and then we should find the proper zeta value, and so this zeta represents the one gain and one pole. Okay, this is the dominant pole, and so which means that the PD or SD is equals to what? 5, 4, 15 plus minus J 10, 57. Okay, and also K gain is equals to what? 125 and this one. Okay, and so where is it coming from? It's coming from root locus. But if we have the information of zeta, and then we can find this blue returns. Okay, nothing more. Okay, we just come here, but if we have these conditions, 20% overshoot, and so we should calculate the zeta. And after that, we draw the root locus in here. The root locus, we have these black lines in here, and so each of the line represent the one values of the zeta. And so we need to find the 0.456 on this root locus, and this blue point is that. Okay?
The root locus will be given as a graph.
Yes, yes, in the method. And after that, at each graph, this intersection point of the red line and the zeta gives us the one root and one gain. This is here. Okay? That's all. Okay. And so, from this information, we need to find new TP values from root locus. Okay? And so, from root locus, we can obtain the information 0.278. Okay? These are uncompensated peak time. And so, how can we apply the step 2 in here? From root locus, we find the peak time, pole, and gain. Okay? And so, what's the condition of this? That the new TP is TP new equals to the what? 0.297 times 2 divided by 3. Where is it coming from? These are the question. 2 of terms, right? And so, if we multiply these terms, and then the new TP must be given in here. In order to set the new TP, we need to set transient response of these terms. Okay? So, before to do that, remember that what is our poles S1 and 2 in terms of the zeta and W1 plus minus Wn zeta square minus 1, and also this is the Wd, okay, from the previous equation. And so this is called damped natural frequency, guys. Okay, where it's coming from the damped, we have zeta values. Okay. And so, from the formulation, damped natural frequency is equals to what? Pi divided by T peak. This is derived from the previous lessons. Just remember that. Also, you have to use in the midterm exam in order to characterize the R time response from here. And so, if we have this information, and then what is the values of the WD in here? Pi divided by 2 divided by 3 times 0.297, which is equal to the 1567. Okay? See? These are the case. And so, if we have this information, and then our desired pole is at 15.78 at the what? Imaginary axis. Right? That's all. If you draw the root locus in here, and so this sigma, this is J, W dot, and so we have this kind of root locus from this system. we will calculate on as well the MATLAB in the previous weeks, okay? And so we have a diagram in here just like this one, and so we have also a zeta values in here on the root locus just like this one, and so this point from root locus right now is equals to what? The k is equals to 101.5, but the pole is 5, 14, 15 plus j 10, 57. And so, what is the meaning of this? This is not our desired pole. We need to move this pole at the what? Imaginary axis to the this one in order to characterize our system. But how we can do that?
By changing k.
Yes, and also we use this geometry. From the geometrical calculation, this is equal to the what? 13 degrees. Just use the geometrical, Pythagorean and the angle rules in here. You can do this because we have the root locus geometry right now, okay? And so, from the geometry, we can write this one. Sigma is equals to what? WD divided by tangential components of the 113 in here. What is the meaning of the sigma in here? We have desired imaginary axis in here, just like this one. And so we have also our sigma components in here, because this must be a right angle, right? And so the tangent values is equals to what? WD divided by sigma, right? Simple geometry. This is the WD, this is the sigma. And so tangent components must give us to this one, right? And also we know the angle of the distance. And then this sigma is equals to minus 13, 8.13. And so this gives us to what? If we want to design the overshoot and the peak time based on the criteria, we need to move the new pole location into the what? Minus 8.13 plus minus j 1572. Okay? If we move the R poles to this location, and so the R peak time is correct, and also overshoot is done with the 20%. Okay? This is our objective right now. Do you get it? Okay. And so, how we can do this? In order to do that, we need to add zeros. Why? Zeros corrects the what? Transient response, as well as peak time, right? That's it. We know it. Because of changing transient time or response. Normally we have right now a desired pole. This one is J1578. Now 87. Okay? And also we have desired poles in here, just like this one, right? These are desired pole. And so, how we can correct this? Because we have the 117 values at this geometry. And so, we need to put this one, this new zero. And this creates the length and also theta values. Okay? And so, the total summation, total angle summation from this system, just remember we add the poles with the negative, we add the zeros with the positive, and so if we calculate this angle summation, is calculated as minus 198.37 degrees. And so we know that all the zeros and pole angles must be equal to the what? 180. And so if this is the case, this number must be subtracted with the 180, and so this degree is obtained in here. And then, what is this degree right now? What is it? This theta is equal to what? This one. See? In order to satisfy the R 180 degree rules, we should add this one, this degree, as a 0, because it must be positive. For example, this degree values is 160. And so, in order to add the new zeros in here, just like this one, minus 20 cannot be added in here. We should give the what? This one. And so, at the right location. Yes?
So, pole negative 813, this is our peak angle, but since it exceeds 180 angles, we add another pole, so we go back to 180. Is this what we're doing?
Yes, but just see this system. We have 3 poles, right? Theta 1, theta 2, theta 3. We have 1 zeros, right? S plus 8. Okay. And so, we have theta 1, theta 2, theta 3, and plus theta Z1, right? This is the pole 1. This is Z1. And if we summate the whole this equation, and then we will get 198.30 degree in here for this pole location. For this pole location. And so how we can correct it? If we add 18 degrees in here, and so it is equal to the what? 108 degree, which means that we need to add the zeros with the degree values of the what? 18. Right? And so, if we have this degree, and so also we have this WD in here, and so we can calculate this one. Right?
So I just have one misconception. Is this happening because we added WD, or is this happening because the geometry of the transfer function was wrong in the beginning?
No, but we drive our desired pole in here, right?
Since we did this, there is...
Yes, and so after that we put this, and so 1587, and also we have the real part in here, and so we put this point, and after that we need to satisfy the angle rule.
So
but how we can do that? This one. And
so, added the peak pole, we need to add another 0 to optimize to 180 degrees.
Yes, and so from the geometry of these terms, we can calculate it. Just like this one. 15,787. And so Z, G, this is the zeros, and also we have 813, which is equals to what? Tangential of this one. 1837 degrees. Right? It's coming from this one. That's all. And so, what is the pole location? Pole is 5592. And so, what is the PD coefficients right now? This is equals to what? S plus 5592. Okay? This is PD design. See? We select the correct D coefficients right now. Do you get it?
Select the correct D, select the correct I.
Huh?
Once we set the D, we can set the I.
Yes, but in the next case we can set that.
So right now, do we have a steady state error?
Yes, and so in order to remove that, in the third step, just see step 3, and so we must add I controller in here, closest to origin, because we satisfy the whole transient response in here right now. Okay? And then how we can do that? GPI S is equals to the S plus 0.5 S. Why do we need to use that? If we add zeros to this system, our angle rule is broken, right? Why? Because we have one more degrees. In order to cancel these terms, we add the S plus 0.5 in here to the closest to the origin. You get it? If we add the 1 zeros pole in here, just see that we have this one, and so if we add the pole, and so this pole adds the another degrees in here, and it breaks the rule, right? We don't have the 180 degrees, and so in order to remove that, we add also another zeros in here, but it's so small, 0.01 for example, or 0.5, and so this is the C, and so this calculation going to the 0 in here, in our assumption.
I have a small question just to understand the geometry. Why is it wrong if we mirror it? So it's like this, and then we have this angle and then this angle. So when we add them, they cancel out. Does that not work?
But the angles summation must be equal to the 180. Okay, and so if we add the I controller, and so we need to cancel it with the small number of these terms, just like this one. You can also select this one is to what? 0.01. But you must do this.
So since the I controller is a pole, we add a 0 very close to it, so it cancels out.
Yes.
Plus minus. Okay.
Yes. But we have added the I controller based on this information. Okay? And so in our case we select this one. So search root locus for this case, which is equals to the ki, or no, k right now, this is the proportional coefficient, is equals to what? 4.6 from the what? From root locus. Okay?
This is the K of our peak.
No. This is the proportional coefficients, Kp. If we add this system, and so we redraw the root locus, and then we should select the proper K values again. In the first case, we have 121, but right now we have 4.6 for the proportional coefficients. And then we have these conditions. PID S is equals to the what? K times S 5592 times S plus 0.5 divided by S. We have this condition. And so we know that from the root locus, if we redraw the root locus based on this information, this system, and so it will give us K 4.6, because in this case zeta 0.5 and also pole is equals to the 8, 12 plus minus 15, 8, 7, J, and also the values of the root locus K 4.6, and so we write 4.6 in here times S plus 5592 S plus 0.5 and divided by S. These are the PID controller. And just remember the formula. If we redraw this the whole distinct terms, just like this one, 4.6 times s square 56 426s plus 27 96 divided by s, and which is equals to the what? Just remember the formula. This is the kd times s square plus kp divided by kd times s plus ki kd divided by s, and so this term is equals to the what? Kd. This term is equals to the what? Kp divided by kd. This term is equals to what? Ki divided by kd. And then we can calculate the whole the coefficients. Kd 4.6, Kp 259.5, Ki is equals to the 128.6. For the what? 20% overshoot, 2/3 of the peak time of the uncompensated system with 0 steady state error. Do you get it right now? The whole the process. At the fourth process, we can design the PID controllers. Okay. Please read 9.6 section in NISA. Okay? For enhance your information. Okay? Any question? It's okay?
It's okay, it's just very long, so it's hard to like remember all the stuff.
Yes, but we will solve these systems on the MATLAB Simulink and the MATLAB script, guys. Okay? But that's all. That's easy. Right? Yes. Or everything must be done in the MATLAB with the theoretical calculations. Okay? You can report to the what or write your reports and the MATLAB simulations to the reports.
By hand,
Yes. Firstly by hand, and after that you will compute the whole results with the MATLAB and compare to both results. Okay?
How will we find the root locus if we calculate by hand?
No, you should use the MATLAB to draw the root locus. You are not to you are not responsible to draw the root locus by hand.
So we will use MATLAB to gain information, but when we calculate differently.
Yes.
So something like this.
Yes.
and then we redo the whole thing with in MATLAB and compare the results to the
Yes.
two processes.
Yes. So let's take a break, and after that we will start the frequency domain. Okay.